So what we have in front of us here are really two main kinds of questions. And if we have time, I don't know if we will, but if we have time, I would like to throw in, oh, something weird going on. Okay, my Norton is telling me it doesn't like something, so let me go in and find out what it is. Nah, nothing. Okay, sorry for that distraction. I didn't see anyone get distracted easily. Okay, so what we're going to be doing is some questions where you do a U-sub first. So you do a substitution, and then you will end up with an integration by parts. We've already seen questions where you start with an integration by parts, and then you finish with a U-sub. We've seen ones that did it that way. So they're kind of switching the process. So it's a mix and match process, and there's 3 questions that do that. And then we're going to finish with well, not finish, but the next thing we're going to do is a thing called the reduction formula. And that is a very special formula where it allows you to find the integral of a whole family of integrals. So you've got one integral formula, but that one allows you to do sine squared, sine cubed, and all of the other guys. And these are, let's check this out. Yeah, okay. So let's jump into question 16. And it has limits of integration. So it has the square root of pi to the square root of pi over 2. And it's 9 theta cubed cosine of theta squared d theta. See if I can get some more light. Just a bit better. Maybe not that one. Okay, give me the U-sub that we should start this question with. Let's just ignore the limits integration until the end. Let's just pretend they're not there. So what U-sub would you use for this integral?
Theta squared.
Right, theta squared it is. So we differentiate theta, or u with respect to theta, get 2 theta. Do the crossover. And then we divide both sides by 2 theta to isolate it. And there is the working for our U-sub. So as I say, we're just going to pretend they're not there for the time being. So it's the integral of 9 theta cubed cosine of u 1 over 2 theta du. And that gets me 9 over 2 theta squared cosine u du. Now, normally we should be really worried because when you do a U-sub, shouldn't all the thetas disappear? That's normally a sign that something's gone wrong if they don't. Can anybody tell me what I should replace this theta squared in terms of u?
Wanted it to be u.
This guy here?
Yeah.
Yes. So it's 9 over 2 u cosine of u. Okay, are we happy now that with this U-sub, the original integral, which really wasn't doable, has now turned into this? But do you recognize that this fella is actually an integration by parts? Does it have that look that integration by parts has? Okay. So we need to pick an f of u and a g of u. Okay, what would the f of u be in this integral?
Cosine.
I wonder why you chose that. If I did use a cosine, then that would make this the g, wouldn't it? And if you integrate this, won't this actually go up in power? So it ends up being uglier than rather than nicer. So if you'd went that way, it would have ended up eventually. You would have seen it. Oh, wait a minute, this isn't going anywhere nice. And probably said, okay, scrub that. So if that one doesn't work, maybe we should use this one. Just switch places. Unless you thought I said what's g of u, in which case you were right. So are we comfortable with the choice of f of u and g of u? Isn't that, I think I called that situation one, wasn't that if it's a polynomial, make that your f? And this is potentially in the polynomial family. So it's derivative. In this case, it's 9/2, and this fella's integral, in which case we get a sine u. And so we can now start putting all the pieces together. This fella is going to be f of u, capital G, f dashed of u, capital G, yeah. And so we're going to have 9/2 u, cosine of u, take away 9/2, cosine of u, du. Would you agree when you look at that line, you know you're on the right tracks? Can you see this integral here much nicer than it was? Right, that's what it used to be. Now it's became something a lot more manageable. So we now have this fella. Integrate that, and has anybody seen my mistake?
You wrote sine instead. Oh, you wrote cosine instead of sine in the second line.
Yeah. There, got it in time. So this guy is going to be plus cosine of u. Technically, we have plus c, which I'm not going to put in this time. So I'll just rewrite that a little bit nicer. We have got 9/2 u we have 9/2 u sine u plus 9/2 cosine u. If there was no limits to integration, in fact, even if there was limits to integration, this is not the finish, is it? I don't leave the answer in terms of u, do I? What should I do?
Plug in theta squared for every u.
That's where we're going now. And if there wasn't any limit of integrations, there'd be a plus c here. Since there is a limit of integration, all I'm going to do now is from theta equals that guy to theta equals that guy. So let's see what we get. We get 9/2 square root of pi squared times the sine of the square root of pi squared plus 9/2 the cosine of the square root of pi squared. Take away All of that with pi upon 2, so I'm just doing that for speed. So that becomes 9 upon 2 pi, the sine of pi, plus 9 upon 2 cosine pi. And when you plug pi upon, square root of pi upon 2 here, you get minus 9 upon 2 pi over 2, sine of pi upon 2. You get take away 9 upon 2, the cosine of pi upon 2. Okay, sine of pi is 0, so that doesn't really matter. Cosine of pi is -1, so that's -9/2. Sine of pi upon 2 is 1. So you get that guy. Cosine of pi upon 2 is 0, so we don't care about that guy. And looks like what we've got here is, if I pull out that fella, there's our answer. So you can imagine there's a fair amount of work in one of these U subs followed by a normal integration by parts. Apart from a little hiccup here, it went fine. Any problems? Okay, start the next one. Version is 17. Oh dear. It's a good question. There's a major problem. If I left it the way it is, I'd be stuck. I know I have to do a U sub. That's what the question tells us. Do a U sub first, and then you can do integration by parts. So they've even told me the technique that I have to use. Yeah, if I look at it as it stands right now, I won't be able to get anything. And you might be thinking, well, why can't you just use cosine t? Well, it doesn't work with the sine 2t that's left. Well, why can't I use the sine of 2t? Because how am I going to get rid of the e, the cosine t? That's what my brain's telling me. How about using a 2t there? Trust me, it doesn't do any good either. All the possible U subs that you could possibly think of that would make any sense at all don't work. So you need to look at this guy and you need to think outside the box. Think of it as a puzzle. I can't really think of anything to do with e to the cosine t. Right, that's pretty much down to the bare bones. But what about the sine of 2t?
The trig identity for 2 sine of t cosine of t.
Right, and I'm just going to stick the 2 there because it looks nicer. Now, they didn't tell you in the question, look for a trig identity, then do a U sub, right? It never gave you all the, it's not going to give you handed on a plate. That's something you had to do. I mean, if you get into that mindset that the only thing you can work with is what you're given to start with, then you're not going to be able to get out of the hole that you're in. You got to be able to look at things and say, okay, that's what I've got, but that's really not what I need. This is what I need. So now I need to pick my U sub because I can do it now. Who is the U sub going to be in this question?
Cosine t.
Correct. Why did you pick it?
Because both things have a cosine t.
Okay, so you saw some here and you saw some here.
Yeah.
E, the ugly guy, gives you cosine t. You know,
Yeah.
Makes sense. So you differentiate it. You get that guy. Yeah, making sure I got my differentiation hat on. That's,
Goes inside.
and that one goes there. And then we'll divide both sides
I
by
didn't
the sine of t. And if you don't mind, I will mute you and you'll hit the space bar. There we go. There we go. So you do this guy over here. So yeah, that looks nice. Let's see how it works. I ignore the integral values, they don't matter right now. So it's going to be 2 e to the u sine t. That guy's going to get me a u. That guy's going to get me a -1 over sine t and a du, and get some cancelling. And when I'm finished, it now looks like that guy. And although you don't know it yet, this one, this integral, is a special case. It is going to be integration by parts. And it is not going to look like any other integration by parts that you've seen yet. This is unique. Okay, so let's see where this unique fella goes. I need to pick an f of u. I need to pick a g of u. Oh, by the way, we're going to go through this question, and it's going to be for the next 5 or 10 minutes, more likely 10 minutes, that you're going to look at this and think, this is going nowhere. Can you just hang in there? It is going to go somewhere. It's not obvious yet what's going to happen. So anyway, give me the f of u guy, give me the g of u. Who should they be, or what should they be?
I have a question.
Yes.
When you did the canceling, why didn't the sine of t values cancel out?
Oh, darn it. You have noticed my deliberate mistake. Once we finish this one, I want to show you how to do that one, because it is a good one. But let's finish on this one. The sine t's do cancel out. I just forgot to do it. Well,
Is
this guy's
there
Then does the u stay?
yes, u stays. Do you think I should just go back to bed today? I think that's what I should do. So after all that mess, we are going to be doing this guy. Of course, I should have realized that. After the u sub, don't we have to do one of these guys? I think what's happening is my brain is still thinking on this guy. And he is a cool question, but he is not this question. So let's just focus on this one. Who are you going to pick as F and who are you going to pick as G for this integration by parts question?
f would be -2u?
Yeah. So this one has got nothing weird going on. In fact, quite easy to integrate. So let's get this fella out the road so I can go to that one that's got my interest. So it's going to be f of u, capital G of u. Keep your eye on me because I pretty much guarantee I'm going to screw up at least one more time before this question's over, because my brain is still thinking of that other one as we speak. So it's this fella, e to the u, -2 times another e to the u. Okay, that came out quite nice. Nothing amazing happened. Integrate that guy. We got that. Would you agree that we're not finished because we have to return to the t's? So it's 2 cosine t e to the cosine t plus 2 e to the cosine t. And then we're meant to evaluate it at t equals 0 to t equals pi. And let's dot that. I kind of rushed through that guy, but I think it was pretty standard one. So let's pick one of the guys that looks like this. Let me pick my own version then. Right, that's the one that got my interest, because the minute I saw it, I thought, oh, I've seen this one, this is sneaky. It is an integration by parts question. So what on earth makes this so special and distracted me so much? Well, let's see what happens. It's going to look like it's going nowhere. But in fact, it is going to lead to an answer. Okay. Who should f of u be? Any suggestions? Who should I pick as f and who should I pick as g?
The only thing that would change the equation at all each time would be if you chose sign for G, right? Because then you'd be swapping like positives and negatives. Otherwise, wouldn't it stay the same?
Well, let's find out. Actually, it doesn't matter. What do I mean by that? Well, I'm just going to pick that as f and that is g. Now, could I make this g? Yep. And would it work? Yes. Will it work this way? Yes. So your picking of f and g is not a problem. Just be consistent. What I mean by that is make sure that the trig guy is f and the exponential is u all the way through this process. Once you've decided to go that way, stick to the trig as one and the exponential guy is the other. Now, if you differentiate this guy, you get 4 cosine u's. And if you integrate this guy, you get e to the u. So let's see what happens to our integral then. It's going to be f of u, g of u, the derivative. This is an amazingly sneaky question. I like this question. All right, so you got 4 sine u's, e to the u. Take away 4 cosine u's, e to the u, the u. Would you agree that this answer isn't much better than the original? In fact, it's a little bit uglier. But you keep going. This bit's okay. It's already going to be whatever it's going to be. This piece here, keep to the consistency. So trig guy goes here. So it's going to be your f of u. And in this case, the exponential is going to be your g of u. So you differentiate this guy, you get -4 sine u. And you integrate this guy, and you get e to the u. So what's our answer going to look like? It's going to be 4 sine u e to the u, take away this guy. Take away f of u, capital G, minus the integral f dashed of u, capital G, du. So it's going to be f of u, that's 4 cosine u's, e to the u. Take away the derivative, and the derivative is this fella. E to the u, du. And so I now have 4 sine u e to the u, take away 4 cosine u e to the u, a negative, and a third negative becomes take away 4 sine u e to the u du. Now at this point, maybe even before this point, you're probably thinking, well, this is going nowhere, because no matter what I do, there's going to be an integral left over. And isn't that integral going to have sines or cosines times an e to the u in it? So that means it'll never end. Right? That would be a reasonable assumption of this problem. Okay. So let's show you the trick. This guy here, let's call him capital I. And we know that this integral, that's him, is here. So what do I know? I know that I is equal to 4 sine u e to the u, take away 4 cosine u's e to the u, take away, what is this guy? Isn't he I? If you add an I to both sides, you now have that. And if you divide both sides by 2, you have that. And just to remind you what I is, I was the original integral that you were trying to find. Now, was it not sneaky? So if you ever see an integral that has a trig and an exponential, so it might be sine of 2u and e to the 4u, doesn't matter. If you ever see a combination of sine and cosines with powers of e, you're going to do integration by parts twice. When you get to the end of the second one, this integral over here will end up being some version of him. And so you will be always able to do this, replace the start and this integral with something to do with I. In this case, I is equal to that. Combine the i's, divide them out, now you got your answer. Oh, come on, that is one sneaky question, isn't it? Unique. No, you don't do that with any other integration by parts I know of at least.
That is very sneaky.
It is. But what that tells me is that within any technique that you use in differentiation and calculus, shouldn't you always be on the lookout for special cases that just don't fit the pattern of the 82 others that you've done? You know, and question number 83 just comes out of the blue and boom. I mean, can you remember doing U-subs where there was a question where you would do a U-sub and then you'd have to do another U-sub on the U-sub to get your answer? In other words, you had to do the process of U-subs twice, right? What we're doing now, because we're getting more techniques is that we have to kind of say, okay, that's a good starting point, but that doesn't mean every question that uses integration by parts is going to end up being the same kind of process, right? There's kind of always going to be this little weird, odd guy out question. So let's move on. This is our second last question for today, version of 18. It's our last U-sub question. Okay, I need a U-sub.
Log X.
Correct. You want to tell the others where that came from, why you chose it?
Well, it was between it or X. And it would make sense for it to be log X because it makes working out sine a lot easier, derivating arc sine a lot easier.
Right, and if you just did u equals x, don't you just change the question to the inverse sine of log u over u du, in which case you're not really changing anything.
That too, yeah,
Yeah.
exactly.
Right, so never, don't have in your list of options u equals x at any time. It just ain't going to work, right? So if you've only got two choices and one of them is u equals x, pick the other one. So in this case, we've got this guy. When you differentiate, you do the crossover. Oh, we got dx right away. So it's going to be, just like you were saying, it's going to be a much nicer looking guy that goes there. Going to be over x times x du. And this time we're going to remember to cancel the x's. Now, don't expect any of these questions to come out smoothly. They will eventually be solvable, but you know, sometimes you have to go quite a few different roads to get to your destination. What do you think we're going to do next?
Integrate.
Yeah, what method are we going to use? You're right. We are going to integrate.
By parts, right? Where inverse sine is f.
And who will G of u be then?
1.
We've seen a couple of examples like that, haven't we? You know, in fact, whenever you have to do an integral that is only one function, isn't the rule make that one function your f and make g1? Remember those? Oh God, what one did we do? I think we did log x, didn't we do log x, for instance? And that was be the same situation. And I do remember doing an inverse sine of some kind. It might have been inverse cosine, but there's the derivative of the inverse sine. So this guy is going to be f of u, capital G of u, take away the integral of f dash du, capital G of u, du. Well, that's good. Let's plug in the pieces. Inverse sine goes first, times a u. The derivative is pretty ugly, times a u du. And all I'm doing here is kind of making it look pretty. Okay, we're here now. That's pretty much done, but we've got this fella, haven't we? We need to find what that guy is. What technique are we going to use to integrate this guy?
You could separate it into u times 1 over square root of negative of minus u squared.
And if you wrote it that way, what's your thought process? What would you be method would you use? When I say method, I mean u sub, integration by parts, power rule, you know, something
Right,
like
right.
that.
And then you could use the integration by parts.
You could try.
Oh wait, no, because we'd have issues with the radical.
Yeah, it would cause some really ugly looking answer, right?
So we could start with substitution.
Okay, then what substitution would be a good one? I'm going to have to call it a v sub because the variable is u.
Yeah,
So what's our v sub going to be?
it's going to be 1 minus u squared.
So let's pause for a minute. We had a question that you had to do a u sub. It turned our question into this, which we had to do integration by parts with. Piece of the answer, this piece, can only be solved by going back into u sub. So essentially, isn't this question going u sub, integration by parts, u sub? And hopefully that's us finished. So I'll differentiate. Do the crossover. The change in letters is distracting me a little bit here. Yeah, that would be a better way. Divide both sides by this fella to isolate the du. Okay, now I've got the guy I want. It's going to be the integral of u square root of v times -1 over 2u dv. The u's are going to cancel, and I'm going to call it -1/2 1 over the square root of v dv. Okay, we're slowly but surely getting towards the end of this question. I still need to integrate this. How am I going to make it happen?
By parts.
Do you know
Sorry.
that would work eventually, but I think I can do it quicker than that, Steph.
Can't you drag the -1/2 out, and the 1 over b would be
I don't know if you can see what that is, but I think the
Oh.
minute you went and said it, that's essentially, I believe that's what you're telling me to do, right? Call
I'm
the
trying
one.
something stupid here.
Oh, well, I thought that's what you meant. Isn't 1 over a square root just a -1/2 power? So it's basically a power rule. So I'm going to add 1 to the power, which makes it +1/2. Dividing by that gets me this, and we're now here. And that's going to become that, and that's going to become that. So if I now return to here, it's u inverse sine of u, take away this guy, and the integral of this guy is him. So you're going to take away a negative, so that's now a plus that guy. And you should be really pleased with yourself if you got to there. And if you type it into WebAssign, it's going to tell you you're wrong. Because I've one more thing to do. Is this the final answer? Is this the way it should look?
Plug back in the x's.
Yeah. So it's going to be natural log of x, inverse sine of the natural log of x, plus 1 take away the natural log of x squared. That question is finished. You know, stick a fork in it is done. That's a lot of work, right? A lot of different things. So you got to have an open mind about how things, especially the more complicated ones, how you may have to do 2 or 3 different techniques. You know, U subs, integration by parts, maybe another U sub, maybe a power roll, whatever it might be. And so be open-minded about, you know, not thinking every single question goes 1, 2, 3, even if a lot of the basic ones do. And this next comment is just me being annoyed. Have you noticed that WebAssign sometimes does the integral of 1 over x and it calls it the natural log of the absolute value of x? You know those guys? Or that you have a question and it's wanting that, and then sometimes it wants that, and sometimes it wants that, and sometimes it wants that. Have you noticed that it sometimes sticks absolute values inside logs, and sometimes it doesn't? And why does that annoy me? If you're going to do the absolute value technique, right, if you're going to stick an absolute value when the answer involves a log, right? So we're talking about the answer has logs in it. If you're going to do that, you might as well be consistent and do it every single time. But don't sometimes do it and sometimes don't, because when that happens, it makes you think that there's a reason why they're doing it, and then there's another reason why they don't do it. And the bottom line is they should do it all the time or never. And I don't like the mixing and matching. I think if you're going to have a rule, you know, stick to it. Me personally, I never write absolute values of x because they're not necessary, really. Why do you have them anyway? Well, can you imagine someone's doing an integral and there were some negative numbers in it? Right, let's take that as an example. Well, we know that the answer is the natural log of x, but you can't put negative numbers into logs. You know that, right? Because negative numbers into logs are a bad idea because the log function doesn't exist. It stops at 0. So if you stick an absolute value in, it lets you use it. That's it. So the only reason you need it is that in some integrals, when you put in the numbers, you might end up with a negative number that's not allowed. So if you make it an absolute value, you'll get a value you can use. That's it. If I went and said to you that the integral was the square root of x minus 1, you would think it a little bit weird that I would stick an absolute value around it. Would you agree? Because nobody ever does that. Why do we not do this kind of rule for other functions? Because in every other function, we normally say, you are not going to use that guy for values of x that wouldn't make sense. Would you agree I would never plug x equals -3 into that square root and expect to get anything simpler? So the way my brain works is, if log is in the answer, I am going to always make the assumption that you would never use that answer with values of x that does not make sense. And we are now moving to our final question. It's called an induction or reduction formula, I should say. And here is that guy. If you want to find the integral of sine cubed, sine 10, sine to the nth power of x, it is -1 over n, the cosine of x. Oh, darn it. I need to do it over here. It's too big a formula to squeeze in that space. So it's going to be -1 over n, the cosine of x, the sine of n minus 1 of x, plus n minus 1 over n, the integral of the sine of n minus 2 of x dx. And it is called a reduction formula. Now this formula has one job and one job only. Its job is to let you find powers of x. It would even eventually, if you had the time and patience, it would even be able to find the integral of that guy. So how do you use this weird reduction formula? Let's try sine cubed. I want to find what the integral of sine cubed is. So I recognize that in this case, n is equal to 3, right? Because it's sine cubed. So every time you see an n here, replace it by 3. So it's -1/3, the cosine of x. Sine n minus 1 becomes 3 take away 1, so that's sine squared. Plus n minus 1 is 2 over n, which is 3, the integral of the sine. 3 take away 2 is 1, so it's just sine x dx. And that means it's this fella, sine squared x, plus, well, I know what that guy is. When you integrate him, you get negative cosine x, and you're finished. Suppose I wanted to do that fella. Well, I'd recognize that n equals 4. I'm going to write the answer underneath because it's pretty big. So what do we get? We get -1/4 cosine of x, the sine of 4 take away 1, so it's cubed, that's that guy, plus 3/4 the integral of sine squared x dx. Now, wait a minute. I don't know the answer to this guy. Right. I knew the answer to sine x, but I don't know the answer to this. How do you think I'm going to get the answer to sine squared x?
Use the reduction formula again.
With n equals 2.
Would it be possible to do it by parts with f of x being sine of x and g of x being sine of x?
You just end up with a version of cos squared when you're finished. So you'd probably be no better off. Although if you did it a second time, you could use that eye trick. I think that might work. I wouldn't do it because it's a lot of work, but I'm not saying it's impossible. You could try it. Never tried, but I'm pretty sure it would be a lot of work. Okay, n equals 2, so it's going to be -1/2 the cosine of x. 2 take away 1 is sine x. That's that bit done. Add 1/2. Okay. What's the sine of x to the power of 0?
One.
So we're pretty much perfect timing. It's that guy. That guy. 3/4 of this guy gets me -3/8. Integrate that, you get an x, so that's a half x. A half times that guy gets me 3/8 of an x. Hopefully I didn't screw anything up. We are finished. Phew. Can't remember who said it, but you know the sine squared x guy? Try doing an integration by parts on that twice and see if you could come up with the answer. If it works, you should eventually get this, you know, if you bring in the 3/4 part. And that is us. Say your last name and bye-bye. Have a nice weekend, everyone.
Professor,
Yes,
I had a question.
sure.
I was gone Thursday, so I just email you. I wasn't gone, but I forgot to type in my last name Thursday. Just email you that I forgot to do that.
Yes,
Okay, sounds good. Thank you.
you're welcome.
On question 18,
Uh-huh.
when we did the V sub,
Yes. Let's see if I can find it.
could we have brought the denominator of the square root of 1 minus u squared out as a power, like -1/2, and then multiplied that by the u that was the numerator?
Okay, let me see if we can find that. So here is the question. Are we talking over here?
Yeah, so yeah, at the top of page 2.
Right. So you're suggesting what other approach? How are you going to do this, guy?
Couldn't you rewrite that as u and then the -1/2 root, the -1/2
Minus
power
u
of
squared to
1
negative half
minus
power.
u squared? Yeah,
You could. What are you going to do next?
multiply the u into, oh no, you can't, because you have to be able to.
Right. Um,
Okay, see, could you do that by parts?
if you tried to do it by parts, the square root of 1 minus u squared would kill you. Its derivative and or integral, and it'd have to be its derivative, I think, would be
Yeah.
really ugly. And so the piece of the integral that you get here, instead of being simpler than this, would be much uglier than this. And that's normally a sign that it's not going to work. Well, you might say, well, could I not switch places, make the other one F and the other one G? Would that help? No, you'd still end up with a different, even uglier looking one.
Yeah.
And so that particular one, this particular one, does lend itself to the U sub technique. I mean, when I see that, I'm thinking, oh yeah, U sub. I know I have to call it V sub, but that's a variable name thing.
Yeah, like I see it because of the u squared in the square root. Like it's like, oh yeah, this is u subland.
Yeah.
I was just trying to think about the other methods and why they would produce ugly answers.
Well, I mean, you through experience, you could try it. I mean, you've got time. If you have time, just try it and see, oh, okay, that didn't work out. I'll not do that the next time I see this. I mean, that's just what experience is. You don't always pick the right answer every time, especially when it's the first time you've seen something. So you're going to practice and you're going to, I wonder if I could maybe do a U sub on this, or I wonder if maybe I could just continue doing integration by parts, because I can imagine a question, where you have to mix and match U subs and integration by parts multiple times. I mean, it would be a pretty ugly question to start with. It did that, but you could end up saying, it didn't happen here. But can you imagine we did a U sub, and what we got was a guy that then needed to have integration by parts done on. And so you would have an integration by parts that created a U sub that then created a different integration by parts, and then you got your answer. So there are all sorts of combinations out there that could kind of come and interfere with your brain. But it's good to do that. It's good to think of questions and say, I wonder if I could do it this way. I've had students do that all the time with me, and I've said, oh, you're right, it could have worked that way, and that way might have even been better, faster. And I like that when that happens. Okay, I'm going to have to kick you out of another class to go to. Have a nice weekend.
Thank you.
Thank you. You too.
Bye-bye.